Welcome to part 2 of the video series Linear Regression, a linear algebra perspective. Today we are going to explore vector spaces further and also discuss subspaces. Now before we get started with the video, I wanted to recommend watching this video at 1.5 or 2x speed. It can help with the experience. However, it really depends on your requirement. Okay, so let's start off. The first thing we are going to discuss is vector spaces. Now, in the previous video, I had discussed this a little bit and had said that Rn space is a vector space. And the reason for that is that Rn space contains or consists of every single n-dimensional vector, right? Now, if you look at R2 space, for example, R2 space will contain every single two-dimensional vector. R3 will contain every single three-dimensional vector. Hence, it's a vector space. However, there is another thing we had touched upon, which I'll talk about in more detail now, which is that every single linear combination of any set of vectors within a space should also result in a vector that's within the same space. Only then is it a vector space. So, LC of vectors of any set of vectors should be within the same space. Within same space. Now, what do I mean by space over here? Space, you could think of it as a set of vectors. Let me explain this with the help of an example. So let's say you had a set of vectors that were all two-dimensional with whole positive numbers and the same number in both components or dimensions. So 1, 1, 2, 2, so on. Example 15, 15, so on. Okay. So all positive whole numbers. Now let's think of this. Is this set of vectors or this space a vector space? Now, the first thing that may come to you is that let's say we added any two vectors within this vector set. Let's say we added these two vectors. You would get the resultant vector would be 3, 3, which is a part of this space, right? But then why is it still a vector space? Let's think of other linear combinations. Okay. Let's say I added 1, 1 plus minus 1 times 2, 2. What would the result be? Any guesses? It would be minus 1, minus 1. And is minus 1 part of the set that only has whole positive in numbers or integers? No. Hence, can you say it's a vector space? No. This is not a vector space. So as soon as you find even a single linear combination or you could even multiply a single vector with any scalar and check if that resultant vector is within the same space. For example, 0.5 times 1. So 0.5 times 1, 1 would give you 0.5, 0.5, right? Let me write that down for you so that you understand it better. So let's say I just took 1, 1, okay, and I said 0.5 times 1, 1. Now you may have the doubt that this is not a linear combination, but you could say it's a linear combination because you're multiplying every other vector by 0. Think of it in that way. Okay, now this is equal to 0.5, 0.5. And is this vector within the vector set we talked about? No. Hence, this is another reason why this set that we talked about, these whole positive number set, is not a vector space. Okay. Now, there are other properties associated with vectors in vector space, like the associative property, the commutative property, but I'm not going to be elaborating on that in this video. All you need to know for now is that a vector space is a space where every single linear combination of any set of vectors will result in a vector within the same space. Okay, only then is it a vector space. Now, I wanted to talk to you about something very interesting, which is vector spaces other than Rn. Okay. Now there are certain vector spaces that don't actually contain vectors. Okay. For example, is M. Now M is a vector space because it contains all 2 cross 2 matrices. So think of it in this way. Try adding any two cross 2 matrices or multiplying them with a scalar value. It is going to result in a 2 cross 2 matrix because the dimensions or the shape of a matrix does not change with addition or multiplication with a scalar. For example, 1, 2, 3, 4 plus 2 times 1, 1, 1, 1 is equal to 3, 5, 4, 6. Yeah. So you see here too, last time I only talked about addition of vectors, but the rule is really the same. You just add corresponding values together. It's just the same thing. You multiply the scalar with every single value within the matrix. Basically the same set of rules follow even for matrices. Now another very interesting vector space is Z or Z, or the zero vector space. Now why is this interesting? We are going to use this concept even later on within the same video. In fact, the zero vector space is the smallest vector space that you can find. Now, some may say, could it be R0? No, because R0 would mean, or rather one would hesitate to call it R0 because R0 means that there'll be zero components. You know, like Rn has n dimensions or n components, R0 would have zero components, but that's not the case with the zero vector space. In fact, every single Rn space has a zero vector, and that creates the zero vector space. For example, R2 would have the zero vector in the form 0, 0, 2 dimensions. R3 would have it with 3 components. It's essentially the same thing, it's just the origin. But it has different, it looks different in different spaces. Okay. Now, why is it a vector space? Give it a thought. You can pause the video and give it a thought. Okay. Let me give the answer now. The reason for it being a vector space is this. Now, the zero vector space only contains one vector. If you add it to itself, if you add 0 to itself, you are going to get 0, 0, right? Any number of dimensions. Yeah. This is going to be 0, 0. Even if there were more dimensions, 3, 4, 5 dimensions, it would be the same. And if you multiply anything with the zero vector, any scalar, let's call it S, it is going to result in 0, 0. Hence, every single linear combination of the zero vector is going to result in the zero vector. Therefore, it is a vector space. I'm just going to call it VS for short. Okay? That's the reason why. Okay, now let's move on to the next topic, which is subspaces. This is again a very important topic. And okay, let's start it off now. The first thing you need to know is this, that very informally, a subspace is a vector space within another vector space. So the rules are the same for a subspace. A subspace has to be a vector space. This means that every LC within the space, every LC result should be within the same space. Okay, because a subspace is also a vector space. Result in the same space, right? Exactly like a vector space. Only difference is it is within another vector space. Yeah. Now you'll start understanding it once I talk about the examples. But before I go to the examples, let me tell you one more thing. Every subspace contains the zero vector space or the zero vector. Okay, we'll talk about this. The zero vector or the zero vector space, you can think of it in both ways, mainly that it will contain the origin. The reason is this. Think of any plane. Okay, let's think of any plane. For example, we thought of a plane in R3 space, which is at a height of z is equal to, here I'm talking about the axis z and not the zero vector space. Okay, here I'm going to say zero vector. Okay, here I'm talking about z, the axis z, the three-dimensional axis z. So let's say z is equal to 5, you have a plane. Okay, so when x and y are 0, z will still be 5 because you are at that height. Yeah. Now the thing is this over here. Let's say you multiplied this vector with 0. Okay, you would get 0, 0, 0. But the origin is not included in that plane at all, because this plane is not sitting at the origin. It is sitting at this height 5. Therefore, you cannot take a plane within the R3 space that does not contain the zero vector. And this is where you might start understanding a question I discussed in the previous video, that why are all two-dimensional vectors not said to be within the R3 space? It's kind of for this reason. Okay, it kind of, you'll start connecting the dots now. Okay, now let's talk about the different subspaces within a vector space. Through that, all these things will start making much more sense. So the first thing I wanted to talk about was the R2 space. Let's start with a very small space. Okay, the R2 vector space. What are its subspaces? So the first one is R2 itself, because it is a vector space, right? So R2 itself is a vector space within the vector space, and therefore it's a subspace. The second is Z, which is the zero vector space, which contains only the origin. Now the third is the interesting one. It's a line that passes through origin, or 0, 0. Okay, this way every vector on that line is always going to be within the line, because if you think of it, if you add any two vectors on the same line, you are going to get a vector on the same line itself. And if you multiply that any vector with a scalar, as we had seen in the previous video, we are going to get a vector on that same line itself. So hence, a line passing through 0, 0 will give you a subspace, because on its own, a line is also a vector space, right? Technically, it is R1, but R1 going through the origin. That's the main point over here. R1 going through 0, 0. Okay. Now, the next example I wanted to talk to you about is the R3 space. Any guesses? Take a break, take a pause, think about it. What all subspaces would R3 have? Any guesses? You can write them down in the comment section if you've paused it and thought about it. But I'll continue with the answer. The answer is number 1, R3 itself. Yeah. Number 2, Z again. Number 3, again, you have a line, but this time it passes through the zero vector 0, 0, 0. Okay. And you have one more subspace over here, which is a plane that passes through 0, 0, 0. Hence, again talking about the same thing we talked about over here on this side, on the left hand side, that you would need a plane going through the origin, because only then will a vector on the plane that's multiplied by 0 continue existing within the plane. So in short, just know this one thing. A subspace is also essentially a vector space, but it exists within this bigger space. Okay, like when we talked about R2, it was just a single plane. It did not exist in R3. Therefore, we could talk about every vector going anywhere. We didn't have to talk about the origin, right? But and that I mean on the plane itself. But in R3, we have to talk about the origin, because the plane within R3 is not going to take care of all the R3 space. It is just a part of the R3 space. Hence, it has to go through the origin. Okay. In case you have any doubts regarding whatever I've spoken about, please let me know in the comment section and I'll try my best to help you out and explain it to you. Okay. So now let us move on to the next thing I wanted to discuss, which is column spaces. This is a kind of a subspace and a very interesting one. Again, all these topics are so interesting. I have so much fun talking about these linear algebra concepts. Okay, so let's start. Now, to be able to understand this, uh, let me say one thing first. The column space is a subspace. Now, you may ask, subspace of what? Is it a subspace of R3? Is it a subspace of Rn? Is it a subspace of a completely different vector space? You'll understand that now. Okay, through the next few minutes, you'll understand what is it a subspace of. So first, I'm going to write down a matrix equation. If you do not remember what a matrix equation looks like, you can go back to the previous video and you'll see how I've multiplied two vectors and represented equations using matrices. Okay, have a look at that first, then it will start making more sense. So let's take this matrix. Okay, 2, 3, 4, 5, 4, 1, 6, 3, then 6, 4, 10, 8. Okay, this is the matrix, and we are multiplying it with x1, x2, x3, which are essentially our variables. So if you think of it in this way, the first two would be 2x1 plus 4x2 plus 6x3, 3x1 plus x2 plus 4x3, so on. Okay, hence you could say that this represents 4 equations with 3 variables each. Okay, and this results in b1, b2, b3. I'm representing the right hand side with variables again. Think of them as constant values. I'm just not giving any value over here for now. Okay, now let's have a look at A. Okay, A consists of 3 column vectors. Okay? 2, 3, 4, 5, then 4, 1, 6, 3, and the third vector is 6, 4, 10, 8. Now the column space is this. Every linear combination of the columns of the matrix create the column space of that matrix. So let's say this matrix is called A, then the column space would be called C of A. Okay, so column space, C stands for column space, and A is the name of the matrix. So all the linear combinations of all the columns within this matrix create the column space of A. Yeah. Now, this is a subspace. I already told you the answer. This is a subspace. But any guesses now? What is it a subspace of? It is a subspace of R4. Now, you may ask, why R4? Any guesses? You can pause the video and think about it. So, it is a subspace of R4 because every single column vector has 4 components or 4 dimensions. And if you think of it in this way, you can even think of it like this, that A has 4 rows. Therefore, 4 components for each and every column vector. Okay, 4 components. Hence, R4. Yeah. So, therefore, you could say that, let's say if there is any matrix M or let me call it M dash, okay, with the shape M cross N, where M is the number of rows and N is the number of columns. You would say that column space of M dash is a subspace of R of M, which is the number of rows. Okay, so if the number of rows are 5, then it's a subspace of R5. Yeah, I hope that makes sense. Now, there's one more thing I wanted to tell you about. If you notice these columns, is there anything interesting about them? Anything that you could observe? So there's one small pattern over here. If you notice, column 1 plus column 2 are equal to column 3. And you could, linearly combine these three in any way. You could say column 1 minus column 3 is equal to minus column 2, or, any way that you want to talk about it. But basically, there are only two independent columns and one dependent column. This means that actually, you only need the linear combinations of any two columns, right? Now, this is where things become interesting. The fact that you only need the linear combination of any two columns means that this is actually a plane. So this, let me just write it over here, two unique columns. Therefore, it represents a plane within R4. Why is it a plane? Think about it. If there are only two vectors, two unique vectors, wouldn't it mean it has a plane? It is actually a plane, because if you think of it, a plane has two axes. Therefore, you would say that if there are two unique vectors within the set of columns that you have in a matrix, you would have a plane, which again goes through 0, 0, 0. Okay? So that's something interesting I wanted to tell you about. Now there's one more interesting thing, which I'm going to leave to you as a question at the end of the video. Let me just write it down. Okay, so first observe this matrix equation. Okay, as I told you, it's 2x1 plus 4x2 plus 6x3. Let me actually write it down in a different way over here. 1 minute. Let me write it down in purple. So you have 2, 3, 4, 5 times x1. Okay, so 2, 3, 4, 5 times x1. You can even write it in this form. I hadn't shown it to you in the previous video. This is another way of writing this. Okay, 4, 1, 6, 3 times x2, right? And plus 6, 4, 10, 8 times x3 is equal to b1, b2, b3. Now my question to you is this. It's based on this another observation. If you notice over here, there are four equations. 2x1 plus 4x2 plus 6x3. Then the second equation is 3x1 plus x2 plus 4x3, and so on. But there are only three variables. This means that either these equations have no solution, so there are no values for x1, x2, x3 that satisfy all four equations, or there could be a solution. Now my question to you is this: when would there be a solution? Give it a thought. I'm going to leave you with this question. When would there be a solution? Or let me rephrase it and give you a small hint too. That for what values of b1, b2, b3 do you think the solution would exist for x1, x2, x3? Give this a thought. It's a very interesting concept. I will start my next video at this point. Okay, so that's it for today's video, and bye, and I hope you have a great week ahead.